Hi, everyone. My name is Farzin Zareian. Today, with the help of my grad student, we're going to talk about statistical variation of seismic damage index of California bridges. This is a project that we have been working on for about a year now, more than a year, and we have a lot to talk about. I am hoping that this guy moves forward. Yes. Before I start, acknowledgements. We have been blessed with peer and Caltrans funding in the past many years, since 2008, that we started working on bridge work with ET at UCLA. And we are blessed to have Boja and Kevin McKee, who were the pioneers of bridge work at peer. I never heard their name this morning. I thought that this would be a nice segue to speak about all the contribution that they had in the early years of peer. So moving forward, our team is made of myself, and Saurabh has done the bulk of the work. We have a great team who is looking over our shoulders to make sure that what we're doing is meaningful. Sharon and folks at Caltrans, Turek, Tony, Amir, Sam, and Mark Mohan unofficially, and Professor Saidia and Professor Abrahamson, who are looking at the stuff from another technical side. Anyway, the work is very much constrained to make sure that what we do is meaningful. And my presentation today has a lot of slides in it. I hope that I can get to the end, that you guys can see what would be the end product of the work that we're presenting here. All right, so we have a hard problem. We need to come up with a performance-based design approach for Caltrans engineers to design ordinary standard bridges. We have two mutually exclusive and collectively exhaustive constraints. The work needs to be comprehensive, and it has to be simple. And simple means should not have too many nonlinear time history analysis, and comprehensive means it has to consider all sorts of variability in the work. And again, I didn't see the peer integral today and the sequence of the variables from IM to EDP to DM to DV, so I thought it would be nice to show them here for you. Now, folks at Caltrans have come up with a process. It's called Probabilistic Damage Control Application. And this is a picture of their, like a title of their paper in ASC Structures, which they have codified some sort of way for designing bridge columns. From the ground motion and loading side, you have the EDP demand. From the damage and decision variable side, you back calculate what is your EDP capacity. Like doing the old engineering way of demand should always be less than capacity, but some probability, let's say, you have a good design. Now, the EDP that these folks are considering is something called a damage index, which is this picture that you see here is a pushover of a bridge column, if you'd like to look at it. Delta Y is the yield point. Delta UC is the ultimate point. The demand that is going to come out of your nonlinear time history analysis or your simplified way of doing the analysis is delta D. Delta D minus delta Y on the numerator divided by delta UC minus delta Y, which is the capacity, it is called the damage index. As you can see, this variable DI, if the loading from the earthquake is small, you are in a really like 50-year return period ground motion. Hopefully you're not reaching yield. So the numerator will be negative. On the same, now on the flip side, if this demand goes beyond delta UC, it is our convention to say delta UC is the end of the life of the column. But unfortunately, bridges and natural beings don't follow what engineers really think that they will do. So life continues after delta UC. So DI can easily be more than 1. But as far as the PDCA work is concerned, DI is constrained between 0 and 1. Anything below 0 is scaled up to be 0, and any DI more than 1 is scaled down to 1. We are doing a lot of massaging of the data, which I'm not showing for the sake of brevity and the time that I have, and I don't want to confuse folks on this. But for today's presentation, DI is log normally distributed, but is between 0 and 1. And that has some impact on the results that I'm going to show, which I'm going to kind of walk you guys through it that you guys can see where we're going. Now, again, continuing with the PDCA approach, it is a reliability probabilistic based approach. So you want to calculate this beta I, which is the closed form solution of a reliability integral. You're integrating probability of demand being more than capacity, condition on capacity on all capacity. And then from there, you get a beta. And then from knowing the beta, you can back calculate what is the probability of failure. Our task is to provide information for engineers that they can do this. So moving forward, let me walk you through the process, and then I'm going to come in and say where our work is important. So the designer comes up with the column properties, size, based on what is needed, and then the experience and everything. And they conduct a simple pushover to find out what is the yield point, ultimate point, and they use, again, simple solution like the ESA, the equivalent static analysis method from SDC, even in SDC2 is there, and come up with a column. The important thing here is that once you calculate the DI for the envisioned column, it has to fall on the 0.35 damage index. Once you have the column, PDCA team is suggesting that a ground motion simulation happens. Ground motions are scaled, which I'm going to discuss this later on in my presentation today. And you get statistics of demand, mean of demand, and dispersion of demand. Obviously, conditional on the SA, which represents the hazard. Continuing with the damage fragility curves that were obtained from lab work, and our work is heavily relying on the work of Sanai and Saidi from UNR and UCLA. And by putting the information that sigma R, mu R, and sigma and mu L and sigma L into this beta equation, you find what is the beta value for each hazard level. And then by integrating over the hazard level, you can basically come up with statistics like what is the probability of exceeding damage state 3 in 75 years? Or what is the probability of exceeding damage state 3 in a 225 hazard level? That kind of statistics can be made. And then if it's satisfactory, unsatisfactory, a bridge will be redesigned or is good to go. And we're going to go for the detailed design. Now, two questions come up and we have the solution. Can demand mean value, which needs to come from nonlinear time history analysis, be determined by the designer using the equivalent static analysis and the fudge factor that we will provide, which is here. And we're going to provide a map of that, and for California. And then we will give canned values of the coefficient of variation across California for DI. This will help the designers not to do too many nonlinear time history analyses and only rely on the small number, which is enough to find the mean, or even if they want to use SDC ESA approach, and then they use our fudge factor to come up with the mean. This is the realm of work that we are doing for this project. So moving forward, we considered 4 regions, and very much Northern California, Central Valley, Bay Area, and then Southern California. The dots that you see on the screen is the dots that we have already completed the work for. And this is up to 2 months ago. We will put columns with a height of 20, 30, 40, 50 feet, axial forces, reinforcement ratios between 1 to 2.5, diameter of the column between 5 to 8, hoop rebar sizes between 5 to 8, and hoop spacings between 3 inches and 8 inches. All combinations are considered. These columns will be evaluated for having a damage state of 0.2 to 0.4. Any column from this that has a damage state of 0.2 to 0.4 in a dot will be considered on that dot for analysis. And we're going to evaluate these columns for 3 hazard levels, 225, 975, and 2475 level hazard. So I repeat what I just said, but now I'm going to slice and dice things in a way that later on you'll see what I mean. The design of these columns we are, for the design of these columns, we're considering damage indices between 0.2 and 0.4. I did mention earlier that the design should be done for 0.35, but we know that a single number is never achievable by an engineer. They might have a design that ends up with a damage index of 0.38. So our work should be comprehensive enough that covers larger than 0.35 and significantly lower than 0.35, which you can enter the zone of over-designed bridges or recovery bridges that they actually have a damage index that is much lower than the ordinary standard bridges. 67 locations so far is the number of dots that I just showed you. We are showing the results for VS30 of 259 in all of those dots. We are repeating the work for 537. We are doing range scaling, so we are simulating ground motions and scaling them up to the target spectrum with range scaling. We're looking at 3 hazard levels. Designs, 51 ground motions per hazard, ends up with 3.1 million analysis, which is 2.5 years of work. If you run it on the PC, we're using our high performance computing at Irvine, which kind of get this thing done in a sort of 2-3 months. We don't have access to what Scott and other folks have at this mega giga Google level supercomputers, but we manage. So I'm going to stop that work. Norm said, I don't believe in the way that you guys are doing your ground motion simulation and then scaling them up. So you need to show me if the work is valid. So what we did is we used something called, in literature, conditional ground motion model. A ground motion model, GMM, is event parameters goes in, intensity measure comes out from the other side. A conditional ground model is not only that the event parameter goes in, another primary intensity measure also goes into the information equation, in the information side of the equation, to give you information about another intensity measure. And these other intensity measures that I'm talking about, we call them secondary intensity measures, are areas intensity and cumulative average velocity, PGV, duration parameters, and all. So what we have done is that, I forgot to mention this, that we are using Armin, Derkurian, and co-workers' work for simulating ground motions. So we go to each one of the dots, we use USGS to aggregate and deaggregate the hazard. We find the main events and their contributions. The events go into a ground motion simulation model, which is stochastic, and generates a motion. This motion definitely doesn't match the target spectrum. So we scale it up to reach the target spectrum. The intention is to find out if this work is valid. So what we do is, I want you to imagine that we are hopping on stones on a pond. We are doing all of our work based on SAT1, let's say. From SAT1, we find the primary intensity measure that is used in the conditional ground motion model to find the secondary IM. So we have SA, we find the primary IM for let's say for CAV is PGA. For areas intensity is PGA and the spectral acceleration at 1 second. This link is done with the conditional spectrum work that Ting and Jack and coworkers have done. And the rest of these, and the IM to primary IM to secondary IM is all done by the work that Norm has done with coworkers. Now, the way that we do the hypothesis testing is that we check for distribution of the parameter, test of the mean of the parameter, and test of the variance of the parameter. The intention is to make sure that what comes out of simulation and scaling gives the same statistics that comes from the conditional ground motion model. And if the 3 tests check, is valid. Otherwise, we go and check if the response is sensitive to the secondary parameter. If it's not sensitive, ignore it. Although that I don't have the ignore arrow here, but imagine that you can ignore that parameter. Otherwise, you have to do a sensitivity analysis and see if the IM that you are generating and is mismatching at least covers the 5 to 95% of the range that the conditional model is suggesting. And the only one that it didn't fit in this ballgame was PGV. So we have considered the following remedy. All the ground motions that we simulate and scale will have a PGV that falls in the 25 to 75% confidence interval of the mean. And the band is between 5% and 95% total. There is no simulated ground motion and scale have a PGV that is less than 5% or more than 95% of what the ground motion, second of the conditional ground motion suggested. Anyway, now let's talk about the maps. And I know that I'm pushing the edge here on time. The slide that you see here is state of California. This is for 225-year return period. All bridges that fall into the design category of 0.2 to 0.4 for damage index are included in this in these plots. I'm showing the fraction of DIs that are less than 0, fraction of DIs that are between 0 and 1, and fraction of DIs more than 1. In this slide, I want you to focus in Central Valley. You see that the heat map is really red. The majority of those columns don't go past beyond 0. They are remaining in the elastic range. In Bay Area, yes, you get into some nonlinear action. But this has direct effect on the statistics that I'm going to later on show for coefficient of variation. Once you assume a log normal distribution, but your numbers are very small, the coefficient of variation goes to huge numbers that are relatively meaningless. So you should stop looking at coefficient of variation and look into probability of failure, which I have at the couple of slides at the end of this presentation. This is the same statistics for 975. Now you see that there is a migration of the red to the center. Now many of our bridge columns are in the damage index between 0 to 1. That means that's yielding is happening, but I'm less than the ultimate point. And obviously some of these guys have reached the post 1, which is collapse, as far as a design engineer is concerned. And for 2475, even further to the right. Now let's take a look at the mean. This is the mean for the damage index for all the columns that are designed between 0.2 and 0.4. I brought in the fragility curves that you guys can make a connection between what is the DI and the different damage states. Damage state 1, 2, 3. Damage state 3 is spalling of concrete. 4 is seeing the rebars, and then 5 is rupture of the rebars. So as you can see, damage, because of that scaling of all the negative DIs to 0, I have a very small numbers in the 225-year return period. Once I get to 975, suddenly some mu is showing up. And then in the 2475, even higher. It's very heartwarming to see that the numbers for Bay Area is larger than the Central Valley from the accuracy standpoint of the work, not from what's going to happen later if an earthquake arrives. Let's talk about the covariance. As I mentioned, because of that assumption of log normal, 9.5 for 225-year return period, 3.47. These are very fictitious numbers. Please don't look at these, but we were just reporting to be fair with the approach that we had. The numbers that are more meaningful to look at are for 975 and 2475, but it is somewhere between 0.4, 0.5, 0.6, which is meaningful. Now, we have also sliced and diced this data for coefficient of variation based on what is the bridge design criteria. The previous slide that you showed was for designs all between 0.2 and 0.4. If we slice the data for designs that are between 0.2 and 0.3, call them over-design bridges, and 0.3 to 0.4, which is, let's say, edge design bridges, we can see that this coefficient of variation becomes smaller up here, which again is due to that scaling up all the numbers from lower than 0 to 0, and more variability happens because of that action. For 2475, again, same idea. I put the slide here for folks who want to watch the videos later on. They can make a comparison. 2 more slides, and then I have the conclusions. This slide is the probability of exceeding damage state 3, which is major spalling. This is the fragility curve for it. We have done the probability of demand exceeding capacity for 225, 975, and 2475. And obviously, you can see that as the intensity, as the ground motion return period is growing, the reds are becoming more. By the way, please make sure that you see that the scales are not similar. Because we wanted to show some heat in each one of these plots, we had to use different scale factors. But again, you see that the maximum here is like 5%, the maximum here is 60%, and maximum here is 90%. In all cases, Bay Area looks worse than the Central. And hopefully when the results of the Los Angeles and San Diego comes up, we can compete with the folks in Bay Area. Integrating the results for each one of the return periods over the hazard curve, we get the mean annual frequency of damage index, damage state 3, which if you put it in a Poisson process and find and do the work, find the probability of exceedance for 75 years, this is what you get. Now, these guys are comparable. You can see that for bridges that are designed to the edge, the chances of exceeding damage state 3 in 75 years becomes close 10%. This is the last slide, and is the drive home message for you that 10% for an edge design bridge, a bridge designed to the limits of the PDCA approach, you're going to end up having 10% probability of exceeding damage state 3 in 75 years. If you over design, the numbers reach around 5%. And looking at all the data together, the picture on the left-hand side shows that. We're not going to stop here. We're going to continue the work until we have the delta L and all the factors for the entire state of California. We're going to also go deeper in areas that we see a lot of variability, and we're going to do some micro zonation, if I can use the word here. We're going to take the work to another level, and we're going to throw bridges in there. We have had 3-4 type of bridges in our arsenal since 2008. We're going to design the bridges for the location and assess the bridges for the location. And we're going to come up with examples for the engineers that they can use the work into their benefit. I hope that I'm not over time. I'm ready to answer questions. Thank you.